Many thanks to Chaire for the prestigious invitation. And so I want to talk about joint work with Mirko Mauri, who happens to be here, and Roberto Pagaria. And also Mirko is particularly precious because all technical questions will be just directly directed to him. And Roberto Pagaria from the University of Bologna. Mirko is from Paris in a sort of École Polytechnique right now. Okay, but not for long. And I also want to thank Mirko for the help in preparing this talk. So what I want to talk about is building on previous work by Ngo and Pierre-Henri Chaudoir and Gérard Lomont, and recent work of Maulik and Shen. So a recent paper of Maulik and Shen is published last year in Geometry and Topology. I wanted to tell you first. This is the starting point. So this is Davek, Maulik, and Julian Shen. And this goes as follows. So C for all the talk will be a projective non-singular curve of genus bigger than or equal to 2. The base field will be C, but this is not really, I mean, it's only for psychological reasons. So in the work of Maulik and Shen, we pick a line bundle on C of degree L bigger than 2G minus 2. So I apologize. I know this is called the Séminaire on geometric representation theory. This is maybe a talk in missing geometric representation theory, because probably some representation theory is lurking behind, but has not been deciphered yet. So now we consider MNDL. So this is the moduli, the coarse moduli space of, well, to be precise, S equivalence classes.
Sorry, interrupt you. Have a problem?
Oh,
just a problem.
Oh no, these are secrets.
Oh, the secret pocket?
No, that's not the secret pocket. It's just
okay. Okay, that's perfect. Sorry.
Okay. Oh, different. So, S equivalence classes, I'll later say what they are, of semi-stable Higgs bundles on C of rank n and degree d. So let me just remind you that these are pairs E theta, where E is a vector bundle, and theta is a twisted endomorphism. Yes, twisted by L. So it's well known that these moduli spaces are quasi-projective varieties, and this is non-singular if rank and degree are coprime, in which case stable is the same as semi-stable. And you know that these quasi-projective varieties are endowed with a natural map H to some affine space, which I will denote by AL. So this is the product of sections of multiples of L. So I goes from 1 to n. And this associates to a Higgs bundle the characteristic polynomial of this twisted endomorphism. So this endomorphism is twisted, so the characteristic polynomial is not really a polynomial. I mean, lives naturally in the total space of L. So we have the total space of L, which is a surface, and inside, for every A in the base, we have CA, which is the locus, the zero locus of the characteristic polynomial. And this is called the spectral curve at A. So we have a family called the spectral curve family over AL. And this family, let me emphasize, does not depend on the degree. It's a flat family, so on a big open set, by Bertini theorem, given this hypothesis, there is a big open set, a dense open set, such that the restriction to this big open set is a smooth map. Now, what Maulik and Shen prove is the following fact, which is quite surprising. The derived direct image of the intersection cohomology complex of M, L, and D does not depend on D. They call this property chi independence. And how do they prove this? Well, the argument is the following. We have this smooth fibration. So let me denote by R1 the local system on the regular part, the local system, so it's R1, I didn't give a name to this, well, let's still call it pi. R1 pi lower star Q restricted to the regular part, so it's a smooth, so this is a local system. So they prove it, what they prove is that this direct image is just the sum of the intersection cohomology of the intermediate extensions, the intersection cohomology complexes of the wedge powers of these with shifts. Well, for perverse shifts, intersection cohomology shifts, and so on, I use the, let's say, the geometric numbering, so not the one in Bellinson-Bernstein-Deligne. So intersection cohomology starts in degrees. The intersection cohomology for the smooth thing is the constant shift. Okay, so it's over complex numbers, but if you do it over, I mean, if you use the constant L-adic shift, this goes just the same. So it's not really relevant. Just I keep complex numbers in mind for psychological, because my training was in complex analysis. So this means that for every D, this is the same complex. This depends only on the spectral curve family. Okay, so I mean, I wanted to emphasize that the spectral curve family doesn't depend on D. So another way to say is that Ngo support theorem, which had already been extended by Chaudoir and Lomon to this case for coprime D, so in the smooth case, actually holds for every D. So this is the so-called chi independence. And it's, I mean, it's what's prompted our curiosity. This assumption is crucial. So we wondered what happens in the critical case. So the critical case is when instead of a line bundle of degree bigger than 2g minus 2, we take L equal to the canonical bundle. So we get what was the original Higgs moduli space, the moduli space of the original moduli space of Higgs bundles. So this is the family of moduli spaces which is relevant in non-abelian Hodge theory, and which is also quite important in the theory of holomorphic symplectic varieties, because these moduli spaces are actually have a hyperkähler, this time over the complex, have a hyperkähler structure. So now I want to discuss what happens here. So since I will discuss only the canonical bundle, I will skip this L from here and skip this L from here, and instead I will put the N just to recall the rank. So we still have all this Hitchin fibration. So in this case, the spectral curve sits inside the total space of the canonical bundle, that is the cotangent bundle of C, which, as we know, as we learn maybe in a course in mechanics, is a symplectic variety. So in particular, its canonical bundle is trivial. Now, together with Heinloth and De Cataldo, we had already observed that something very different happens. So let me just say that, for example, the intersection cohomology, in this case, the intersection cohomology of the moduli space of rank 2 and degree 0 is different from the intersection cohomology of rank 2 and degree 1. Okay, so something like this cannot hold. And there is a clear reason, and the reason is that there's no such isomorphism. There are more summands in the decomposition theorem which depend on the degree. So with the Cataldo-Heinloth, we had already examined this fact. So I want to sketch this result because it's quite relevant. So here we are in the co-prime case, so the moduli space is non-singular. So let me introduce some notation. So I denote by AN red. Red stays for reduced, not for the color, inside N. So this is the locus where the spectral curve is reduced. Which contains, of course, the regular locus. And, well, which contains also the elliptic locus. Now, fix N, a partition of N, okay, so we have the a sort of stratification of the Hitchin base. Well, let's say, let me define this set. So these are the points in the Hitchin base. such that the spectral curve splits as the union of R irreducible components. R is the length of the partition. Ci maps to C with degree ni. And also we require that Ci are non-singular and Ci intersect Cj is transverse. So it's a nodal curve with non-singular irreducible components. By the way, the cardinality of this intersection is 2 and I and j g minus 1. Okay, so what we prove is the following. So what we proved is that for every partition, there exists a local system, a non-trivial and non-zero local system, which I will denote by Ln, with rank equal to the length of the partition, with finite monodromy, actually, I'll say later what the monodromy is, such that, okay, so if n is the trivial partition, so if n is the trivial partition, this Sn is the regular locus. So if n is the trivial partition, this Ln is just the constant sheaf, such that, let me write the decomposition theorem as follows. So I'm talking about the co-prime case. So in this case, intersection cohomology is just the constant sheaf. So this one is the sum over all partitions of objects, which I will denote by this way. So these are now commonly called Ngo strings. Not my fault, sorry about that. And so these are constructed as follows. So over this locus, if you restrict the spectral family to this strata, you see all the curves have this structure. So if you consider the relative Picard, this is for every point an extension by a product of multiplicative groups of an abelian group scheme, which is basically the peak zero. So there's some degree fixed here, which is the peak zero of the normalization. Okay, so you have let's say you have an abelian scheme. Well, a torsor over an abelian scheme over Sn here. And, well, call this guy Gn. So these strings are, well, let me be a bit abusive. IH of R Gn lower star of Q tensor Ln. So by this, I mean the following. You have an abelian scheme, so this guy actually splits as a sum of wedge powers of the first direct image, okay, with shifts. So when I say IH, I mean that I applied intermediate extensions of over all summons. Okay, so this particular structure that the action of this abelian scheme gives this particular structure to the decomposition theorem is what is dealt with in the paragraph, which I like very much, in the paper of Ngô, which is called Cap Produit et Liberté, if I interpret it well. Okay, so this term here is just the string for the trivial partition. But then over all stratum, there is a whole string supported there. So in a sense, Ngô theorem, that is, that there are no supports over the elliptic locus, is just as large for the case in which the twist is by the canonical bundle, is just as large as it can be. As soon as you go out, I'm sorry, I forgot something. This is not true. This is only over. I wish this was so. But as my title says, this is only over the reduced locus. I would tend to conjecture that this holds everywhere, but I have no real evidence except rank 2, I guess. So you see there's a completely different behavior from the case in which the twist is by a degree which exceeds 2g minus 2. Let me say a few things about the monodromy of these local systems. So the pi1 of this strata surjects into the stabilizer of the partition. So if you have a partition, you can act on the rows of the partitions, and many times it won't give you a partition. So you'll have a non-trivial group only if you have some blocks of the same length. So the stabilizer of the well, if you write n as 1 to the a1 in the multiplicative notation, then the stabilizer of n is the product of the symmetric groups over the thickness of the partition. Okay, so these local systems are just given by representation of the stabilizer of n, and the rank of the partition, the rank of the local system is the length of the partition. So actually one can say precisely what they are. So you take the representation of the symmetric groups on our objects, which is induced by the maximal cyclic subgroup by a primitive character, and you take the induced representation, and you restrict it to the stabilizer, and this is precisely the representation which gives you the local system. And I want to say just a word on how this is proved, because it's relevant to what we did afterwards. So let me skip some reduction which leads one to understand only what happens on the nodal locus, where the spectral curves are nodal. So let me denote by this the locus where spectral curves are nodal. And one observes that these spectral curves are stable in the sense of the Lin-Mumford. So we have a classifying map over the Lin-Mumford compactification of curves of genus, which is n squared g minus 1 plus 1. Maybe one should say over the Lin-Mumford stack. And over this, the Lin-Mumford stack, there is a universal compactified Jacobian of some degree. So there is a degree which, by the Boville-Riemann correspondence, which is some degree which gives you a Higgs by direct image from the spectral curve to see a Higgs bundle of the right degree. So this d prime is something by Riemann-Roch plus n squared minus n g minus 1 plus or minus, I don't remember. And by the Boville-Riemann construction, the fiber product here is just the isomorphic to the restriction to the nodal locus here. Now, what happens is that this map is of full support. Full support in the sense, I say before, that in the decomposition theorem, all the summands are supported over all the base. Okay? So by base change, since this guy here is smooth, so this is the constant sheaf, so if I base change, I take the direct image of the constant sheaf. What I have to understand is how this behaves. So what I have to understand is how intersection cohomology behaves with respect to pullback. And in general, it doesn't behave well at all. And let me sketch an example which I like very much. I find it quite enlightening. So, toy model. Let's consider a curve. I mean, this is not a Hitchin fibration. Hitchin fibration requires too many dimensions to be drawn. So let's take a curve consisting of two rational curves meeting at 2 points. And let's take what is called the versal deformation. So in this case, I'll have two axes over which one node persists and one is smoothed. And over the whole regular locus, you have just a smooth elliptic curve. Now, if you compute the direct image of the constant sheaf here, you find Q shifted by -2, and intersection homology of the local system R1. And if you shifted by -1. If you compute intersection homology of this guy here, there are no support. Everything is supported on the whole basis. Okay, and in this case, there's a recipe to compute intersection cohomology, and you find that intersection cohomology has a non-vanishing first cohomology sheaf at 0. And this non-vanishing, well, it's actually equal to Q. And this non-vanishing first cohomology is precisely accounts for the fact that there is an extra component. Okay. Now, the analog of the Hitchin fibration is just to pull back by a disk which is not transverse to this stratification, but which passes through the origin. So when you pull back, you still get a smooth sorry, I'm shifting to the complex picture, but I shouldn't. You still get a total space which is smooth, but if you pull back IH of R1, this cannot be IH of the pullback of the local system, because by the support condition for intersection cohomology, this guy over a curve has to be a sheaf, so it's not allowed to have a higher cohomology sheaf. So the only possibility is that when you pull back this splits off as summoned. And this is precisely how the supports in the theorem of with the Cataldo-Heinloth are born. So the geometric meaning of the Hitchin fibration is that for the case of the canonical bundle, the map, the classifying map in the moduli space is not transversal. It's actually as non-transversal as it can be in order that the pullback is a smooth space. But it's not transverse, and this means that when you restrict the intersection cohomology shifts, the highest cohomology shift in the standard cohomology shift of this intersection cohomology complex has to split off and create a support. And this is just
But it has some kind of transversality, because if you take any curve,
I mean, it has to have some kind of transversality, otherwise there's a mess. But so, you know that the Hitchin fibration is smooth. So, you know that the restriction of this intersection cohomology complexes has to stay perverse and semi-simple, because the decomposition theorem has to hold. But so the only way out is that the restriction of these intersection cohomology shifts on the big base are split off the summand. So this is just the only mechanism. You're not convinced?
No, in general, I don't know what happened. In your example?
This is I mean, in the work of with the Cataldo-Heinloth, we proved precisely that this is what happens if you consider this thing, then it always splits off the highest cohomology shift of these intersections. Okay. And this is precisely the difference between twisting by KC and twisting by L. If you twist by a bigger line bundle, then this map is big enough so that the restriction of the intersection cohomology is intersection cohomology of the restriction. And so why, I mean, your support theorem holds. Well, so with Mirko, and later with Mirko and Roberto, we asked ourselves, so what happens for other degrees? So if the degree is not coprime. And I think the answer is quite amusing and quite funny. So I have to make a premise of a technical nature. So even though M and D for N and D not coprime is singular, the decomposition theorem for the direct image of the intersection cohomology has the same structure. I will say what I mean as in the coprime case. And by structure, I mean that this guy still is a sum of some Go strings with, for some objects here. And so this mechanism that you have a local system and you can twist it by the Jacobians of the normalizations on the strata. And this follows from two facts which are quite important. So the first fact is that the standard truncation in degree bigger than twice the relative dimension, well, relative dimension, so dimension of M minus dimension of the base, of this guy is 0. This is, I mean, it has to be checked by a computation. And I mean, in our case, KC, this depends on the symplectic structure of the Hitchin fibration. So on the fact that the Hitchin fibration is a Lagrangian fibration, and the restriction to the singular part is again a Lagrangian fibration. And second, that the top cohomology sheaf is just equal to the top cohomology sheaf of the direct image of Q. And this is important because this guy, as we learned from Bảo Châu, can be understood reasonably because this over just any point, the stock at any point has the irreducible components of H minus 1 of A as a basis. Okay, so this is the top cohomology of the constant sheaf, so it's generated by the irreducible component. So it's something which can be reasonably understood geometrically. Okay, so let me tell you what we find. Oh, I also should add that similar results in a higher generality and with high-tech tools are being pursued by Ben Davison and Encar and Schlegel-Meyer and his school. And probably Olivier Schiffman talked about similar things in your seminar, well, maybe 1 year ago or something like that. There's things related to the cohomological whole algebras and something like that. So we take a more artisanal point of view. So let me make some a trivial remark. So now I have my D, which is an integer, and I have a partition of n. So I say that n is the integral if ni d over n is integral for all I. Okay? So for example, if d equals 1 and n is bigger than 1, only the trivial partition is integral, if D equals 0, every partition is integral. So if, I mean, this of course depends only on the greatest common divisor of D and N. And well, maybe let's take just an explicit example. So if D, well, in this case D can be 0, 1, which are already been treated, and 2, so the partitions are 4, 3, 1, 2, 2, 2, 1, 1, 1, 1, 1, 1. So for D equals to 2, this is the only, I mean, this is always integral, this is integral, and the other aren't. Okay, that's trivial, but it's good to have it in mind. So this notion has an obvious geometric relevance, because if N is the integral, I can consider the product of the Hitchin moduli spaces Ni with rank Ni and degree dNi over N, and map it to the big moduli space by the direct sum operation. So this maps into the product of the bases. And here I map to the base. This is why I wanted to keep the rank here, by the multiplication. So you see that the image of this guy here lands inside what I had first denoted by Sn. So I'm considering spectral curves which splits as factors, not necessarily irreducible, of degree Ni. And here I'm landing inside Higgs bundles, which are direct sum of Higgs bundles of lower ranks with the same slope. And the singular locus of M and D is precisely given by this image, by the union of these images. So the notion of D integral is a partition is D integral if the corresponding stratum in the base contains a whole, well, to have a real stratification, it should be refined a bit. It contains a whole stratum of singularities here. Now, the theorem which we proved with Mirko Mauri and Roberto Pagaria is the following. MMP, so I'm very glad to write MMP, which once in a lifetime doesn't mean minimal model program, which is a nightmare for, for some algebraic geometers like me. So for every non-integral, non-D-integral partition N, there is a local system L and D, more or less with the same property on Sn nodal, such that the direct image of the intersection complex of M and D, again on the reduced part, is the sum of the Ngo strings, local, non-zero local system, of the Ngo strings of these local systems. well, so this is the sum of this partition non-integral, well, plus I have to put the integral the trivial partition which gives the fully supported thing. So for varying D, you only select the non-integral strata as support. And these things here have an explicit description. As representations of the stabilizer of the partition. So just to give you an idea, I think it's good that I write down an example. I already have it here. Oh, in particular, if D equals 0, so the degree 0 Hitchin moduli space, so the one that in the non-abelian Hodge theory corresponds to, I mean, bona fide representations of the fundamental group, not twisted, every partition is integral, and therefore we have that it's at least on the reduced part, the direct image is fully supported. So we have two extrema, D equals 0, full support, D coprime, every possible support. And in general, it's intermediate behavior. So, so I put here, so let's say that D, as I said, can be 0, 1, and 2. Oh, by the way, this description also makes clear that at least on the reduced part, the behavior depends only on the greatest common divisor of D and N, as conjectured. So let me write down here, so the stabilizer of the partition, well, here is the trivial group, here is the trivial group, here is the symmetric product of two elements, here is the symmetric product of two elements, and there's the symmetric product on 4 elements. So in degree 0, as I said, there is only the support. So here I write the rank of this L and D. In degree 1, as I said, the rank is the length of the partition. So 1, 2, 2, 3, 4. No, sorry, I wrote something wrong. So in the De Cataldo thing, the rank of Ln is the length of the partition minus 1 factorial. Sorry, I screwed it down. So this is 4 minus 1 factorial, 6. Okay, in this case, so this is the only thing here. So here, 2, 2 is D integral, so there is no support here. Otherwise, the supports are, and here is, sorry, I screwed up the ranks. 1, 2. Okay, here the support is, the rank is the same. Here is 0, here is 1, and here is 3. So the ranks behave, I mean, they are, for D, general D, they are sub-representations of the representation of the coprime case. So I think this is on the reduced locus as complete a description as one can hope. So now I have to make a difficult choice, because in these remaining 11 minutes I have to choose whether to tell you how one proves this, I mean the main line how one proves these theorems, or I have to give a philosophical explanation of this thing. So let me see. Well, I prefer philosophy. So you see from this theorem, there is a balance between the strata. If the partition identifying Sn is non-integral, then you have non-d-integral, you have a support. If it's d-integral, you have this, this whole thing of singularities inside. So this is the image of this product of smaller Hitchin fibration. So either the inverse image of a stratum hosts a singular stratum of this kind, or it's a support. So what is the explanation? The explanation goes back to what Maulik and Shen were doing. So we go back to the classifying map with on the compactified moduli space here. Now we have, well, this is actually a stack, but doesn't really matter. This chi doesn't depend on D. And over this stack, you have all the possible compactified Jacobians families for all possible degrees. Okay? And the several Hitchin fibrations, at least on the nodal locus, but this is what is relevant, are obtained as fiber product from one of these. So we should have these maps, but it's a fact which in a way is similar to Maulik and Shen results, that the inverse image, the direct image of the intersection cohomology complexes of all these compactified Jacobians, they all satisfy full support. Okay? They are all of full supports, and therefore this object is independent of D. Then, since chi doesn't depend on D as well, the pullback of these objects is independent of D. So what is this object? Well, so in the case that D equals 1, or so in the coprime case, then this is just the constant shift. So by proper base change, this is just the direct image of the Hitchin map. But otherwise, this is just the direct image of something which looks really bad, which is the intersection homology of the compactified Jacobian restricted, the intersection homology complex of the compactified Jacobian restricted to the M and D. So again, we are back to the fact that, I mean, just as in the work of the Cataldo-Einlot, we have to understand what happens when you restrict an intersection homology complex to a subvariety. But anyhow, whatever that is, this direct image is independent of D. Now, there is a suggestion from another galaxy which there should be such an object whose direct image is independent of D, and this is called the BPS sheaf. There is a conjectural definition by Davesh Maulik again and Toda. And so this guy here should be, precisely, so the intuition is that in the Fano case, that is when L is bigger than 2G minus 2, which is called the Fano case because the total space of the line bundle is has ample anticanonical bundle, the intersection homology is the BPS sheaf. Otherwise, there should, in the Calabi-Yau case, like this, there should be a perverse semi-simple sheaf which has this independence property. This happens to be perverse semi-simple. We can prove it. And it's actually pure. If everything could be upgraded to the language of mixed Hodge models over complex numbers or Eliadic elsewhere, and this happens to be pure object. So this is a proposal for the BPS. I was thinking this morning that there's a perfect Italian expression, which I don't know how to translate, BPS ed enoantri, some sort of poor man BPS, of BPS sheaf for the working class. I don't know how to put it. It's just a modest proposal for BPS. Now, something which is, I'm about to finish, quite remarkable is that this can be studied. The structure of this sheaf can be studied because there is a local model for M and D, let's say, inside the compactified Jacobian around points in this singular strata here. Say generic points. I don't want to be too precise here. And this local model is the following. There is here something which is called the affine Lorentz variety. So this is a toric variety which is associated to the graph, to a graph. Which graph do we take? We take gamma, the dual graph of a spectral curve, of a generic spectral curve CA, where A is in the stratum we are looking at. So this graph in general is a complete graph because every component in the spectral curve meets, but in the edges, between two vertices, you have to put twice an I and J G minus 1 because it's the intersection, okay? So it's a complete graph with multiple edges. So out of this graph, you construct a toric variety, an affine toric variety, singular affine toric variety. And this variety here contains something which is what is called a hypertoric variety. So these varieties are really computable. And the model is precisely that along general points in this singular stratum here, the embedding looks like this embedding. And if you do some more study here, this affine Lorentz variety happily happens to have a resolution which is small, such that the restriction gives you a resolution of this hypertoric variety, which is semi-small. Okay, and this is a local model up to multiplication by trivial things for this embedding. So if I want to see how the intersection homology of the compactified Jacobian restricts to the Hitchin moduli space, it's enough to understand how intersection homology of this restricts to this. But since this is small, intersection homology of this guy is the direct image of the constant shift here, so I can base change, and so it's a direct image of these semi-small maps. And semi-small maps are really easy to understand. I mean, the decomposition theorem for semi-small map is easy to understand. We know what the strata are. These are called the relevant strata. And in this case, so we can really compute this intersection homology. And in particular, 0, these are cones, so they have a selected origin. Over 0, the inverse image here has middle dimension irreducible components, and guess what? How many irreducible components you have? This is precisely the rank of the local system. So this completes this sort of balance. In this mysterious object, non-integral partitions give you support. Integral partitions don't give you support, but it's intersection homology which creates precisely the missing part. So you have actually local systems over this, over an open part of this. I don't want to be too precise because it's late. And these local systems are actually pulled back from the Hitchin basis, and those are precisely the local systems which appear in general. So I think this balance gives sort of a harmonic view to everything. I think I stop here. Thanks a lot.